I was telling is geometrically, what does a linearly dependent set mean is what someone asked. So suppose we have a set of two vectors, v1, v2. When do we say this set is dependent?
When
One
one
is
is
a
scalar
scalar
multiplication.
multiplication of other.
Yeah. So one of it is a scalar multiple of the other. So if I have a vector v1, v2 is going to be along the same direction of v1, right? Means it's along the same line. v2 is going to lie on this line. Now, suppose I have three vectors, v1, v2, v3. Let's take three vectors in R3. When will this set be linearly dependent?
When they will
One
lie
of
in
the-
same space, same
When
plane.
at least one of them is a linear combination of the other vectors, right?
Yes.
It is possible that v1 is equal to alpha v2 and v3 is equal to some beta v2. That is, v1 and v3 are both
Yes, ma'am.
dependent on v2. This is possible. Or v1 and v2 are independent and v3 is dependent on them. That is also possible, right?
Yes, ma'am.
Yeah. So if v1 and v3 are both dependent on v2, how is it going to look like? v2 is some vector in R3. v1 is alpha times v2. So where will v1 lie?
Ma'am, both will be extension of V2s. Right?
So they will be on the same line of v2, right?
I'll be scaled.
Ma'am,
Yeah.
one case is also possible that v1 plus v2 is a scalar multiplication of v3.
Yeah. So this was that case. v1, v2. Suppose v1, v2 is independent and v3 is alpha times v1 plus beta times v2 or something like this. This is also possible, right?
Yes, ma'am.
This is one case. This is another case. So if v1 and v3 are both scalar multiples of v2, they are all going to lie on one line. Agreed?
Yes, ma'am.
Now suppose v1 and v2 are linearly independent. What will I get out of it? By generating v1 and v2?
Alpha beta
By
is equal to
generating it, I
0.
am going to get a plane, right? With two vectors,
Yes,
I
plane.
can generate a plane.
Yes.
Yeah.
Yes,
And we know that because v3 is in this linear combination, v3 lies on this plane. That is what we know, right?
Yes.
Yes, ma'am.
Yeah. So is it now clear what geometrically dependence means?
Yes, ma'am.
Yes, ma'am.
Yeah.
Mhm.
Okay.
And why superset of linearly dependent set is dependent?
So you now consider the same set, v1, v2, v3. You already know v3 is a linear combination of v1 and v2, right?
Yes.
Now if I add any other vector, is it going to make a difference? Because v3 is already a linear combination of v1 and v2, right?
Okay.
That is why a superset of a linearly dependent set is dependent.
Okay. Thank you, ma'am. I have just.
Ma'am, that doesn't matter that V4 lie in the same plane or not.
It doesn't matter, no? v4 can be independent. It doesn't matter. Yeah.
Okay.
We just want one of the elements in the set to be a linear combination of the some other elements. And that is anyway happening by v3.
Okay, ma'am.
Yeah. So you all recall what a vector space is?
Yes, madam.
Yes.
Yes, ma'am.
So vector space is nothing but a set with two operations, plus addition and dot scalar multiplication, that satisfies a list of 10 conditions, right? Closure with respect to addition, closure with respect to scalar multiplication, 4 conditions with respect to addition, 4 conditions with respect to scalar multiplication, right?
Yes.
Yes, ma'am.
So that is a vector space, and then we have what is called as a subspace. A subspace is nothing but a subset which is also a vector space.
With respect to same operations.
Yeah, with respect to the same addition and same scalar multiplication. And to check if something is a subspace or not, it is enough if we check only 3 conditions. Closed with respect to addition, closed with respect to scalar multiplication, and whether the 0 vector belongs to the subspace or not. And what is a linearly dependent set? Linearly independent set.
if all the coefficients are 0. Only
Ah.
possible case is 0.
Yeah. So a linearly
Linear
independent set.
combination.
Linearly independent set means you are not allowed, means all the vectors in the set, none of the vectors in the set can be written as a linear combination of the other vectors. So if you have a set of n vectors, then none of the vectors can be written as a linear combination of the others. So how will we write it mathematically is that if we write 0 as a linear combination of these vectors, then this should imply that all the coefficients are 0. We already know this, right? 0 v1 plus 0 v2 plus etc. plus 0 vn is equal to 0. This we already know, right?
Yes.
Yeah. If this is the only way of writing it, then the set is linearly independent. If it is not linearly independent, it is linearly dependent, right?
Yes.
And if we have 2 vectors in R2 or 3 vectors in R3, how will we check independence?
Determinant.
Determinant.
Matrix.
You'll just create
Determinant
matrix
Row
for
reduction or determinant.
with the vectors as columns, and then we will
Determinant.
find the determinant of the matrix. If the determinant is non-zero,
Non-zero. Yes, ma'am.
then it is a linearly independent set.
Independent.
So all this we had discussed earlier. So in week 4 content, we have what is called as a spanning set. So
Ma'am?
what is a spanning set? Yes.
Yes, one more doubt. Like if A is M by N matrix, and if M and N, how can M and N depend? Like if M is greater than N,
Mm.
how it can affect dependency and independency?
Okay.
Like if
So-
three condition, like if M is N, M is greater than N, M is less than N, and M
A is the matrix formed by the vectors, right? Whatever vectors are given,
yes,
right?
yes,
Okay. So suppose if M is equal to N, then you do the determinant thing, right?
yes, yes, ma'am.
If determinant is equal to 0, then independent. Dependent. Determinant is not equal to 0, it is independent.
Not equal to 0. Yeah.
If determinant is equal to 0, it is dependent. And then now suppose M is greater than N. So the
Yes.
number of rows is greater than the number of columns. Like this, right?
Yes.
So in this case, it may be dependent, it may be independent. In this case, it's independent, right?
Yes.
This is one vector, this is another vector. Is the second vector a scalar multiple of the first vector?
No.
So in this case, it is independent. Whereas if you take this, in this case, it is dependent, right?
Yes.
Yeah. Now what about the other case? So when M is greater than N, we cannot tell anything. Now when N is greater than M, so the number of vectors is greater than the number of rows.
And ma'am, in this earlier example, how many maximum independence vector is possible if M is greater than N?
If M is greater than N, how many maximum?
Independence.
You cannot tell, no? Means if you can have say how many maximum independent vectors is possible. See, in this case you have 2. In this case, okay, if you say maximum, then it is M, right?
Yes.
Not M, N.
N.
Number of vectors is N. Yeah. N vectors also may be independent, right?
Yes.
Maximum will be n or n minus 1.
It can be N, no? Because M is anyway greater than N.
Yes.
So it can have N independent vectors, no? Like in this case.
Yes.
2.
Madam, in
No, actually, I think he was asking about independent variable.
Variables or vectors?
No, vector. I'm
Okay,
just
okay.
asking independent.
Then it is.
Yes.
Ma'am, can we find the dependency by row echelon, reduced row echelon form?
Yes, yes.
How, ma'am? How can we do that?
So, was that not? Oh, it was not a part of the content. Okay, fine. So you can do row echelon form, and then you find out. So if you get a pivot in each column, you put the vectors as columns. You do row echelon form, and then if you get a pivot in each column, it means that all those columns are independent.
If columns got pivot elements in them,
Huh,
then they are independent.
Yeah.
Okay.
Ma'am, last
Yeah.
condition.
This will
N.
come into picture when we generate bases, I guess. Yeah. Yeah. When you talk about bases, all this comes into the picture.
Ma'am, last condition. If n is greater than m.
If n is greater than m, so you have more vectors than the number of coordinates in each vector, right?
Yes.
So in that case, what happens?
Always dependent.
Always
Dependent.
dependent.
It's always dependent. Something like this. Right? This is one.
Madam,
Huh.
excuse me, madam.
Yeah.
Madam, in above condition, if at m greater than n, if we have 10 rows and 9 columns, and find and ask that which vector is dependent, then how can we find the particular vector is a dependence or not?
When you convert it into reduced row echelon form, you will actually know which vector, and you can even write down the linear combination from the reduced row echelon form. Say for example,
Okay.
this we will discuss all this later. When you're studying about basis for null space, you will study all this in detail.
Ma'am,
So,
in third condition, why always dependent?
because see, when the number of rows denotes which space the vector comes from, right?
Yes.
So it is coming from Rm, right?
Yes. Yes.
And if you have more than m vectors in Rm, it is always going to be dependent, right?
Okay.
3 vectors in R2 are always linearly dependent, right?
Yes.
Like that. So n vectors in Rm is always going to be dependent when n is greater than m, right?
Yes.
That is why. Is it clear?
Yes,
madam.
Yes. Thank you.
Thank you,
So
madam.
we proceed to what is a spanning set. So spanning set, in some sense, you can think of it as a generating set. That's all. What is the set generating? That is a spanning set. Okay. So span, if you're given a set of vectors, say 2 vectors, span of this set is all possible finite linear combinations. So how will linear combination of a set of 2 vectors look like? How will linear combination of this set look like?
Alpha V1 plus beta V2.
Alpha V1 plus beta V2 equals 0. So.
No, why 0? I'm just asking for a linear combination.
Okay.
Yeah. If you want to write 0 as a linear combination of these 2 vectors, then you will put equal to 0. But this is how a linear combination of V1 and V2 will look like, right?
Yes, right.
Yeah. So you consider all such possible linear combinations. Alpha can be anything, beta can be anything.
Here,
So if you take this set,
here dependence and independence doesn't matter.
no, we are not talking about dependence, independence at all. We are just talking about the span of a set. The set may be linearly independent, dependent, it doesn't matter. So span is just this. It is the set of all possible linear combinations of these 2 vectors. That's all. So this is going to be the span of this set. You take all possible linear combinations. Whatever possible coefficients for V1 and V2 are there, all that will be included. So first question is, does V1 belong to span of V1, V2?
Yes, ma'am.
Yes.
How can you write V1
Yes,
as
ma'am.
a linear combination?
1 into V1 plus 0 into V2.
Perfect. So we can write V1 as a linear combination of V1 and V2. So definitely V1 belongs to the span. Like that, V2 also belongs to the span, right?
Yes.
All the elements of a set naturally belong to the span of the set, right? Agreed?
Yes, ma'am.
Yes, sir.
Yes, ma'am.
Okay. But span of a set is this general thing. We look at all possible linear combinations. We can do any alpha, beta. Okay, so that is what span of a set is. So the span of a set of
Can we say V1 plus V2 is belongs to span?
definitely. You put alpha is equal to 1, beta is equal to 1, you're going to get
Madam,
V1
can we
plus
say V1?
What was someone asking? Can we say?
V1 plus V2 is also the span of V1, V2 vectors.
No. See, V belongs to the span. Yes, V1 plus V2 belongs to span. Span of a set of vectors is another set, right? This is a set, right?
Yes, ma'am.
Yeah.
Yes, yes.
Yes, V1 plus V2 belongs to the span because I'll put alpha is equal to 1, beta is equal to 1, right? Like that, V1 minus V2
Yes.
also belongs to the set, right?
Oh, yes, madam.
Yeah. Okay. Yeah, so span of a set is nothing but the set of all linear combinations of the elements that we are considering in the set.
Ma'am, can you geometrically also?
Yeah, I'll tell. So span is nothing but you're trying to find all possible linear combinations. So that's what I was talking about here, right? So what is span of V1, V2? If I have a linearly independent set, if I have V1 and V2 here, this is V1 and this is V2. When I span this, when I take all possible linear combinations of this, what am I generating?
Plane, V2 plane in a
Plane.
R2 plane.
If you have one information or one direction, you can generate a line, right?
Yes.
If you have two directions, you can generate a plane, right?
Plane. Yeah.
By generating, what are you doing? Means, how are you generating?
V1 plus V2.
Not just V1 plus V2.
Taking all the linear combinations.
That is what geometrically span means.
Yes.
You're taking all possible linear combinations. If you have three directions, what can you generate?
Space.
So R3
Yeah. Yeah, you can generate R3
Yes,
or
space.
a three-dimensional subspace of whatever is the space you're considering, right?
Yes.
So,
yes.
so considering this this equation,
Ah.
so minus subtraction of alpha V1 minus beta V2 will also be a valid
Yes.
span.
Yes. Alpha and beta can be any real number. Positive,
Okay, so,
negative, zero, anything.
So linear combination means that any alpha, any beta with
Yeah.
any type of arithmetic operation.
Addition and scalar multiplication. That's all. These are the only two operations allowed.
But you are telling like alpha V1 minus beta V2 will also.
Oh, minus can be seen as -1 plus -1 times V2, right?
Okay. Okay.
So this is considered scalar multiplication and addition.
Okay.
So in a vector space, the only things we do is scalar multiplication and addition.
Okay.
Yeah. Does 0 belong to the span of V1, V2?
Yes, ma'am.
How
Yes,
does
madam.
it belong?
Alpha and beta.
0 V1 plus 0 V2.
Yeah. You'll take alpha and beta to be 0. That's all. 0 V1 plus 0 V2. So this is 0 always belongs to span of any set. So in fact, you can prove that if S is any set, not necessarily a subspace, S is any subset of V means span of S is always a subspace of V. If S is a subspace, naturally span of S is a subspace. But if S is just a set also, span of S is always going to be a subspace.
I didn't get this point.
So I just take one vector, V1. What is span of V1? What did I say? If you have one direction, when you span, what do you get?
From every scalar multiplication
Straight line?
of itself.
Line.
Line.
In fact, a line passing through the origin, right?
Yes, ma'am. Yes, ma'am.
And do we know that lines passing through the origin are subspaces?
Yes.
Yes, ma'am.
Yeah. So span of one vector is going to give me a line. That is a subspace. Span of two vectors. What did you tell me? Span of two vectors.
A line or a plane.
Line
Plane.
or a plane. Perfect.
Yes.
If it is a linearly dependent set, it will be a line. If it is an
Line. Otherwise,
independent
it will-
set, you will get a plane. And will the plane pass through the origin?
Ma'am, it can be.
It will always, no? 0 always belongs.
Oh,
to
yes, 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 ma'am. Yes, ma'am.
So it will be a plane passing through the origin or a line passing through the origin. Are they subspaces?
Yes, ma'am.
Yes, ma'am.
Yeah. So if you look geometrically, it is easier to see that span of a set will always be a subspace.
Okay,
Now is
ma'am.
this clear?
And, ma'am, and S subset of V.
S can be any subset of V. Am I taking a
Okay,
subspace?
okay.
I'm just taking one element, right?
Okay.
Yeah, this
From
is
V1, V2, any subset can be a subspace of V.
You
in a
take
span.
any set, you find its span, you will get a subspace.
Oh, okay.
Ma'am, suppose if two vectors are there, V1, V2,
Ah,
and if we span them, we can get a line or plane.
yeah.
And when we'll have that line, ma'am?
Line if V1 and V2 are dependent, no?
Dependent.
V1 is alpha times V2.
Oh, so scalar multiple. Okay, okay,
Ah,
got it.
ah.
Got it, ma'am.
Yeah. Okay. So is the concept of span clear? You're just generating a subset, subspace, starting from a
Yes.
subset. Yeah.
Then here V is what?
Tell me. Here V is
Here V is what? Is it a space or a
vector
vector?
space. Vector space.
Because in here one line we are taking as a vector and then as span we are considering as a subspace. So that's why I clarified.
No. Suppose V is a vector space. Is R2 a vector space?
Yes.
S is equal to 1, 0. Is this a subspace of R2?
No, ma'am.
Yes. Yes.
Yes, ma'am. Yes, ma'am.
No, how is this a subspace? 1, 0 belong to S?
No, ma'am. No, ma'am.
So this is not a subspace.
Ma'am, why, ma'am?
Subs
2, 0.
Subspace means what? Alpha times elements should also belong to the set, right?
Yes, ma'am.
Does 2, 0 belong to this set?
No, ma'am.
Ma'am, only 1, 0 belonging to
Huh.
this.
So it is not a subspace, no? Can any single point be a subspace of R2?
Yes, ma'am.
Yes,
No, ma'am.
if it is
No, ma'am.
0, 0.
No, ma'am.
If it is 0, 0.
0, 0. Yeah. Yes.
Only this. Other than that, nothing else is possible. Now, what is span of S?
A linear combination.
All possible linear combinations of elements of S, right?
X axis.
You'll get the x-axis, right?
Yes.
Is the x-axis a subspace?
Yes.
Yes.
No, ma'am.
Why not? It's a line passing through the origin, right?
Yes, ma'am.
And we know lines passing through the origin are subspaces, right?
Yes.
If you add two elements from the x-axis, the output is also going to be an element of the x-axis, right?
Yes.
When you multiply, do scalar multiplication of an element in the x-axis, again it's going to be on the x-axis, right?
Yes.
So it is a subspace. So now is it clear that this is a subset, but the span is always going to be a subspace?
Ma'am, but the scalar multiplication of S is 2, 0. Suppose then it is also belonging to X line.
To the x-axis,
Then why not?
yes.
Then why not subspace?
No. S is singleton 1, 0. S has only one element.
Okay. When element is not defined, then we can say.
Element is not defined means?
Ma'am, means when we don't know about the element.
Linearly independent.
Yes, ma'am.
Singleton
Can you
set.
please repeat that?
Or
And when the element is not defined, I mean it can be anything like X or X and 0. Then we can say.
Yeah. If it says x, 0, where x can be any real number, then it is yes. This is x-axis, right?
Okay.
So this is a subspace. What is span of this S, sir? What is span of x-axis?
1 0.
That is a comma 0, where a is
1
a belongs to R.
0.
No, span of x-axis is x-axis itself,
Axis
right?
is itself, right?
Yes.
So ma'am, basically span of S is that set builder form notation, and S is that roster form elements of span S.
Repeat. Which one? This one or this one?
No,
The first
I'm
example
saying
or the second
span
example?
S is the set builder form of entire notations of all the coordinates in the x-axis, and whereas S is, we are explicitly mentioning each element of the x-axis. Right?
No. Which one? Which one are you telling? This one, is it? Second example.
Yes, ma'am.
No. If I write x-axis here, even then it's the same. Span of x-axis is x-axis itself, right? Does x-axis generate any other point, say 1, generate again the x-axis itself, right? If I just pick one element on the x-axis and take the span, that is also going to give me the x-axis, right?
Okay.
What is span of 1, 1? Just this element.
Plane.
A plane in x, y.
1, 1 on plane.
Line
Y equal to X.
You will get y is equal
Straight
to
line.
x, right?
Across origin.
Yeah, you have the point 1, 1. Span means what? You're taking all possible linear combinations. All possible linear combinations is going to look like this: alpha times 1, 1, right? Where alpha can be any number. Will 2, 2 belong to span of this set?
Yes.
Because it can be written as 2 times 1, 1. Right? So you're going to get this line.
But we can separate 1, 1 by alpha multiplied by 1, 0 plus beta 0, 1. This is
Agreed,
also a
but
linear
my
combination.
set is not that, no?
Here set is only 1.
My set is 1, 1. So I'm looking for linear combinations of 1, 1. I cannot write 1, 1 as a linear combination of something.
Ma'am, but what is the span of 1, 0?
X-axis, no?
Exactly.
It's alpha
Then-
times
then-
1, 0.
Then ma'am, 2, 0 is also a span.
2, 0?
Yes, ma'am.
Is
In
also-
the span of 2. In the span of 2. Oh, sorry, 1, 0.
Yes.
Yes, ma'am. Then why it is not a subspace?
No. Is S a subspace? That is the question. Span of S is always a subspace. It's
Yes.
the-
Okay. Ma'am.
What is span of this set?
Entire X line.
X-axis.
Again x-axis. Yeah.
Span of a zero vector, the point.
You're not going to get anything, no? If you take S is equal to 0, 0, then alpha times 0, 0 is always going to be 0, 0, no? Whatever be alpha.
Yeah, so it's a point.
Yeah. Is it a subspace?
Yes, no?
The 0
Yes,
vector.
Yes, ma'am.
Yes.
Yes, ma'am.
It's just the 0 vector. So this is always a subspace. So whatever be
Is
the
our-
set S, span of S is always a subspace. Is it clear?
Yes.
Yes, madam.
Yes, ma'am. Yes, ma'am.
Okay. So now we have a set.
But madam, vice versa not possible, na? If the span of X is a x-axis, then we cannot say that S is a subspace of a vector V.
No. Here we have span of S is x-axis. Here also we have span of S is x-axis. Here we have a subspace. Here we don't have a subspace. Right?
Okay, got it, madam.
Yeah.
Okay.
What is span of 1, 1 and 1, 0?
X, y.
It's a plane, ma'am.
What plane?
Parabola.
XY.
X comma Y.
XY plane.
It is R2,
X,
right?
Y. R2, yeah, R2, ma'am.
Why?
Because every point.
Because
of
they are
R2
not,
will lie
I
in
mean,
this.
one cannot be written as a scalar multiple. They
Yeah.
are not dependent.
Yeah, they are not on the same line. So definitely they are going to generate a plane. And they are all in R2. So the plane that we know is R2 itself, right?
Yes, ma'am.
But how will we check this? How can you prove this?
1, 1 minus 1, 0.
1, 1 minus 1, 0 will give what? Then what happens from there?
Then we will get another vector 0, minus 1, 0, 1.
Then?
We will get a linear combination, and through that we can expand our set.
Okay, fine. So what do you want to prove? Do you agree that span of 1, 1 and 1, 0 is a subset of R2?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
So if you want to
Yes,
prove
ma'am.
these two are equal, I want to show the other way, right? When can you say two sets are equal?
When A is equal to B as well as B is equal to A.
Every element is an element of other, ma'am.
A is
B is
A
a
subset
subset
of B as well as B is subset
B,
of A.
yeah. Yes.
Yeah. So this
Then
one
both
we
sets
all
are equal.
Now I want to show the other one. I want to show that any element in R2 can be belongs to this span, right?
Yes.
How does an element in the span look like? Span of these two elements means how does it
ma'am,
look like?
you are
Linear
saying
combination?
that any element from R2 is a linear combination of elements of span of that set. Is it?
If we can show that, then R2 is equal to the span, right?
Okay, means you are saying about spanning set.
No, I've still not told what a spanning set is. I'm just trying to tell.
Okay.
You agree that span of these two vectors is R2, right?
Yes, ma'am.
Yes, ma'am.
And you also agree that span of this set is definitely a subset of R2, right?
Yes,
madam. Yes, ma'am.
To prove it is equal, I have to show the other inclusion also, right?
Yes, ma'am.
Yes, ma'am.
So I pick any element in R2. If I can tell that it belongs to the span of these two elements, then we are done, right?
Yes, yes, ma'am.
So how does span of these two elements look like? How does this set look like?
Linear combination of these two, ma'am.
Yeah.
Alpha
times 1,
1 plus beta times 1, 0.
If I can find out alpha and beta in terms of x and y, I am done, right?
Yes, ma'am.
Yes, ma'am.
So
Can we do
alpha plus
that?
beta is x, yes, ma'am.
Yeah. Alpha plus beta is x
And alpha is y.
alpha is y.
So
So we
beta
know
is
what
x
is
minus
beta.
y.
Yeah.
Yeah, x minus y.
And how
So
this
span of this set. What is span of this set?
every possible
Linear combination.
linear combination of this.
Is this a linear combination?
Yes, ma'am.
I want to check whether every element in R2 can be written as a linear combination of these two elements, right?
Yes, ma'am.
I'm just checking that if I find out alpha and beta, I'm done, right?
No, ma'am. Alpha plus beta is equal to x and alpha is equal to y. How can this?
Oh, I'm just doing vector scalar multiplication and then addition.
Oh, okay. Sorry.
Alpha comma alpha plus.
Yes, ma'am. Yes. Okay.
Yeah. So can I find out alpha and beta from here?
Yes, ma'am.
Yeah. X comma
Ma'am,
y.
can in the span set all the elements will be independent of each other?
No, not necessarily. Like
Ma'am, if we are like in this set, these two are independent. If we add another element, it may be it always be dependent.
Right.
If we are talking about R2 span, then there must be two elements independent of each other.
If I want to get a basis, yes. Otherwise, no.
Okay.
Okay. That was a good question. Now tell me what is span of 1, 1, 1, 0, and 2, 1.
Not possible.
Why not?
I mean R2.
R3.
R2.
No, it cannot be R3.
plane.
We are all in R2.
May I, ma'am? May I?
Yes, please.
1 comma 1 plus 2 in 2 scalar multiplied by 1 0. 1 comma 0.
So, what does that give?
That will give 2 comma 1.
Okay. No, I'm asking what is the span of this set?
I think the plane again.
1 comma 1.
See,
Plane, R2 plane.
Plane
R2, right?
Yes, ma'am.
Yes, ma'am.
So I have added one more set, one more vector to this set. But is that going to change the span?
No, ma'am.
No, ma'am.
No, madam.
No, ma'am.
No, ma'am.
No. Why?
Because if earlier it was R2 and now it is also R2.
So earlier I was using these two vectors to generate. If I have two vectors, two directions, I can generate a plane, right?
Yes.
Yes, ma'am.
Yes.
So with these two vectors itself, I can generate a plane. So whatever vector I add after that is unnecessary, right?
Yes.
Yes, ma'am. There
Yes,
are two
madam.
unknowns and we are knowing two values to find them. So only two are necessary. Rest are redundant.
Yeah, exactly. That's where that basis comes into the picture.
But when two vectors are aligned, then the third vector can affect to the span.
Agreed.
Yes.
Now tell me this. Can you write x comma y as a linear combination of these two vectors?
Yes.
Yes, madam.
Quickly
Alpha
tell me what
alpha
it
1
is.
1 plus alpha 1 1 plus
What is alpha?
beta
What is beta?
1
Y and
2 alpha
of Y of 1.
We already know this, no? We already found this out, right? X minus y times 1
at
comma
last
1.
0 into 2 comma 1.
Yeah, plus 0 into 2 comma 1. You can have other linear combinations also. But this is one of it, right?
Hello, madam. I don't understand that 2 comma 1 means when we add that, then we will get R2 plane.
Okay. Can you get anything more than R2? Tell me that first.
No, how to?
No, madam.
No, ma'am.
Yes,
Never.
I don't understand that.
Can you do alpha times 1 comma 1 and get a vector with 3 components?
No.
No.
So we are going to stay in R2. Is that clear?
Okay, means we are getting two coordinates.
We are not going to go to R3 or R4 or anywhere. We are going to stay in R2.
Okay.
Yeah. And to,
Then,
to understand any point in R2, say x comma y, how many directions do you need to know?
2 directions.
Yeah.
Only 2 directions.
why 2 directions?
You need to know what the x component is when y component is, right?
Means,
You need to know how far you have to go on the x-axis.
yes.
How far you have to go on the y-axis.
Yes, yes.
Can you please
Could you
mute if
please
you're not
mute
talking
the-
to me?
Same thing with sigma square. Okay. Sigma square will always represent the variance case. It's the random variable x is clear from the context. So clearly sigma is the standard deviation. This is mu and sigma. This is again and again and again. And statistics cases of variance. So if there are multiple random variables, if you want to refer to a particular random variable, you simply add a subset. Okay, mu sub x.
Yeah. So you need to know how far you have to go on the x-axis or how far you have to go on the y-axis. You need to know both to reach this point, right?
Yes.
But is it only along x-axis and y-axis? If you know how far you can go here and then how far you can go here. From here also you can get information about this x and y, right?
From where?
XY plane.
Like this. What were the two vectors? 1, 1 and 1, 0. Okay, fine. So if I take 1 comma 1, if I take this direction and then I take this direction, can I reach this point x comma y with just this information?
Yes. Yes, we can.
Yeah, means you go diagonally, you go straight, you go left, right, you go in any direction. If you know 2 directions, you're going to reach any point, right?
Yes.
Yeah.
Yes, ma'am.
So you basically need two directions to reach any point in R2. Agree?
Yes.
That is what we were discussing. So what was your question? Why did we come here?
Why after adding 2 comma 1 we are getting the same
Okay. So two vectors are enough, right?
And what if I
Yes.
have 2
Third
comma 1?
vector, 1 second. The third vector is not going to give me any extra information, right?
Yeah, it is also giving x direction and y direction only.
Like this. See, any point x comma y can be written as x minus y into 1 comma 1.
Ma'am,
Plus,
why 1 comma 1 होगा?
no, that is because I chose that set. I randomly chose a set 1 comma 1, 1 comma 0. So if you're looking for span of this set, you're looking for linear combination of these two vectors, right? Not any other vector.
Yes, ma'am.
That's why.
But ma'am,
But
we
here
can
alpha equals to y and beta equals to x minus y.
Oh. Sorry. Alpha is y.
Yes, madam. I have also same doubt.
Okay. That was my fault. Plus x minus y. Now is it okay?
Yeah.
Okay.
ma'am, we can also write it as the linear combination of 1 1 and 2 1 also.
Exactly. Fine. No problem at all. You can also write this as alpha times 1 comma 1 plus 0 times 1 comma 0 plus beta times 2 comma 1 and solve for alpha and beta. No problem.
Okay.
But can you write it as alpha times 1 comma 1 plus 0 times 1 comma 0 plus 0 times 2 comma 1?
No, no, ma'am, no.
No. Any point in R2 cannot be written as alpha times 1 comma 1. For example, 2 comma 1 cannot be written as alpha times 1 comma 1, right?
Yes, madam.
You need at least two directions.
Madam, if 2 comma 1 we consider that only one point, then it will span whole R2, right?
No. How will 2 comma 1 span whole R2? What is span of 2 comma 1?
Because this point we can go in R2, means in the direction.
No, you tell me what is span of 2 comma 1.
R2.
Not R2.
Linear single line.
What is
Yeah.
span?
Only.
How will you write down span of 2 comma 1? What is that set?
Alpha into 2 comma 1.
That's all, right?
Yes.
Can you write 3 comma 5 as an element here?
No, ma'am.
No.
So how can you tell that it is R2? This is an element in R2 which does not belong to this set, right?
Yes.
But then I can define a vector space and then define the spanning.
How will you define vector space?
No, I mean, I'm just asking, like, since it's R, we say that it's not a spanning set, right? But if I have my own vector space, then it's already defined, then still I can have a spanning set for a vector space.
I did not understand. You are telling you can make this as a spanning set of some R2 with some other addition and some other scalar multiplication, is it? Maybe.
No, ma'am, it can't
If your
be.
addition.
It can't be a spanning set of R2.
No,
Actually.
it can't be a spanning space of R2, but I can define my own vector space and.
Yeah, you can define your vector space as span of this set, right?
But that vector space can only include alpha of this 2 1 and nothing else. That is span.
Ma'am,
Is there any case?
Like you were asking the spanning of 2 comma 1, so it will be always the multiplication of that 2 comma 1. Or let us say, like, if it is 4 and 2, like similarly I can say that is a spanning. And even 3 comma 5, it is a R2 vector because it contains two dimensions like x and y. It is a R2 one, but it is not a spanning of 2 comma 1 because it is not a multiple of 2 comma 1.
Yeah.
Okay, thank you, ma'am.
Any other questions?
Ma'am,
Ma'am, is there any case where the span of some vectors is not equal to the, I mean, it's not the subspace of corresponding R2 or R3? Just
No,
like that.
span of a set is always a subspace. That's what I was telling you.
Subspace of, ma'am, subspace of what?
Subspace of the vector space that you started with. You start with a subset of some vector space, right? Only then you start with a subset, right?
Yes, yes.
Of what? Subset of what? The span will be a subspace of that whatever vector space you started off with.
Oh, okay, okay. That is a subspace, but it is not necessary that that span of S is equal to that vector space.
No. I'm not telling that
yes.
span of S is equal to V.
Yes,
if
ma'am.
that happens, then S is called a spanning set.
Yes.
It is a spanning set for this vector space.
Yes, ma'am. I was asking, I mean, is there any case where it is not equal to the vector space?
Yeah, we can just take this, no?
Not for a singleton set. If you take at least two, and both are not scalar multiplication of each other. Two or more. You can take two or more.
In R2, is it?
Yes, in R2. Let's take.
In R2, once you pick a second vector which is not a scalar multiple of this, it's going to generate R2, right?
Oh, then it is always a spanning set of R2.
Yeah.
If the two vectors are linearly independent. Yes, that is if you have found a direction which is away from this direction.
Yes. If they are dependent, then it is not.
Say for example 2, 1 and 4, 2. What is the span of this set?
Span is 2x equal to y, the line.
Yeah, you're going to get a line only. You're not going to get R2, right? Even though you have two vectors.
Yes. And if you add some more vectors?
If I add 3, not 3, 6, 3.
No,
it's still going to be that line, right?
Oh, some another vector which is not a scalar multiplication.
Once you bring in a second direction, it's going to give you R2, no?
Okay. It is still a dependent set. I mean, dependent, linearly dependent.
Yeah. Say for example, I add 1, 2. Now what's the span of the set?
Whole R2.
Whole R2.
R2.
Yeah.
R2.
Yes, ma'am.
But it's still a dependent set, right?
So
Yes,
it is not a spanning set.
Why is it not a spanning set? Spanning set has question of.
I'm asking.
No, it is a spanning set. It is a spanning set for R2. No?
Any set of any span of R2 is a spanning set.
If you take a set, subset, and then its span is equal to R2, then it is called a spanning set.
Yes,
you take any set, if it spans a vector space, it is called a spanning set. For that vector space. Spanning
Yes, madam. All the above examples were of spanning set.
Ma'am, in the
this is not a spanning set. This is a spanning set. This is a spanning set.
Ma'am.
Yeah.
Which one was not spanning set, madam?
This one.
Yes.
Because span of this is not equal to R2, no?
Okay.
Yeah.
This 2, 1, 4, 2 and 1, 2. You said it is not a spanning set, right?
No, it is a spanning set.
Ma'am, how do you define that spanning set and not a spanning set? Can you please elaborate that?
What is it? Can you please repeat?
How do we define that it is a spanning set and it is not a spanning set? Could you please?
Spanning set means span of that set should be equal to the vector space that you started with. If you take the span of this set, are you getting R2?
Yes, ma'am.
So it is a spanning set. That's all.
Ma'am, in the just above that one is a spanning set, right? Like alpha. No, the two. Can you just scroll down? Yeah. No, that it was three vectors.
This one.
Yes.
Ah.
It's a spanning set, right?
Yes, because span of that set is R2.
Yes, ma'am.
Spanning set for what you should tell? For that vector space R2, whatever the vector space is.
And ma'am, how do you know that span of something is R2? I mean, span of this set?
So,
just by looking those vectors?
Just by looking you want to know, or mathematically?
Both. Let's.
For R2, to get R2, you need two directions which are different, right?
Yes, ma'am.
1, 1 gives you one direction. Does 1, 0 give the same direction?
No.
So it's a spanning set. You got
Okay,
two directions, it's going to span R2.
Okay, if at least a pair is not,
yeah,
I mean, have both have
don't
some,
lie on the same line. Yeah.
Yes. Okay.
And mathematically here we have done. You pick any element in R2 and you should be able to express it as a linear combination of those vectors.
Oh, yes. Ma'am.
Yeah. So is it clear what a spanning set is, what span of a set is?
Yes, ma'am.
Yes, ma'am.
Ma'am, can you reiterate these two lines once again so that we can have
So the summary is this. Span of a set is set of all linear combinations of elements of S. And the span of a set of any set is always a subspace. Fine?
Yes, madam.
That spanning set, that S is said to be a spanning set if its span gives you the entire vector space. Span of S can be any subspace.
So is that also imply that out of 3 or out of 4, one should be independent? Like it can be expressed as 0? It can, so that it can give you other than the line.
Yeah. For R2, you need at least two elements, right? To span R2, at least two directions, in the sense that two vectors which don't lie one on top of the other, right? You need at least
span
two
of S is a subspace of V, right?
Yeah, it's a subspace of V.
Okay.
Ma'am, there will be an infinitely many span set for a vector.
Agreed. Spanning set you mean, right?
Yeah.
Spanning set for a vector space. Yeah. See.
Ma'am, I have a doubt.
One minute. What is span of 1, 0?
X-axis.
X-axis.
All the points lie on x-axis.
So, do you agree that 1, 0 is a spanning set for x-axis?
Yes, ma'am.
Yes, ma'am.
Absolutely.
Yeah. Is 2, 0 a spanning set for x-axis?
Yes, ma'am.
Yes, ma'am.
Is any n, 0 a spanning set for x-axis?
Yes, ma'am.
Yes, ma'am.
Is 1, 0, 2, 0 a spanning set for x-axis?
Yes, ma'am.
Yes, ma'am.
Yes.
So once you get a spanning set, you can generate infinitely many spanning sets, right? Take union, take scalar multiples, all that, right?
Madam, can you explain for 2, 0 is spanning x-axis?
Well, all these are still in R2, right?
Yeah. These are all in R2, but the vector space I've considered here is x-axis, the subspace.
But ma'am, 1, 0, then 2, 0, and something 3, 1 is not a spanning set of that x-axis.
Yeah. Once you put some other vector, it's not going to span just x-axis, right? What was your set? 1, 0, 2, 0, and then
3, 1.
What does this span? Does this span x-axis?
No.
R2.
R2.
Ma'am, can you say 2, 0 is spanning x-axis? Why?
So the question is this a spanning set for x-axis?
And also, why it is span of x-axis?
Yes.
Yeah. So spanning set of x-axis means what? Span of 2, 0 should be x-axis. Agreed? If this is the case, then 2, 0 is a spanning set for x-axis. How does any element in the x-axis look like?
A, 0.
Can you get A, 0 just by using 2, 0 as a linear combination? How does linear combination of 2, 0 look like?
1, 0 plus 1, 0.
No.
Alpha into 2.
Alpha into 2, 0.
2, 0, yeah.
What should this alpha be?
A by 2.
Can you generate any A, 0 using 2, 0? Yes. By putting the coefficient as A by 2.
Okay,
Linear combination means what? It should be in the form alpha times V1 plus beta times V2 plus gamma times V3, like that, right? Here we have only one vector. So it's going to be alpha times that vector.
Okay, ma'am. Thank you.
Yeah. So is it clear what a spanning set is, what span of a set is, and all that?
Yes.
Ma'am, one small doubt here. Ma'am, like here we need to consider if it is a different vector. Let us say 1, 0, 2, 0, it is only same. That is only the spanning of 1, 0, 1, 0 x-axis. But K1, it is a different vector. So it is considered as spanning the R2 space, right? But agar, like if it is there again another vector which will be having another, let us say, so can we, it cannot be in R3, right, at any moment. It can be in R2 or it can be spanning of x-axis only. The moment
not just x-axis, any line. It can be any line. It depends on what the vectors are.
Okay, so ma'am, then for R3, then it needs to be have minimum 3 elements in it, in that set itself. Let us say
not 3 elements, 3 components.
Components.
See, what
like
is
1, 0, 1.
What is span of 1, 0, 0? First of all, where does this lie? R2 or R3 or R or
R3, ma'am.
R3.
What is this?
X-axis.
X, Y, and
in
Z.
R3.
It is the x-axis in R3, right?
Yes, x-axis in R3. Yes.
What is span of 1, 0, 0, 0, 1, 0? Where does this lie?
XY plane.
Plane in R3.
First
It
one
is
is X
again
and
in
second
R3.
is
And this is the XY plane, right?
Yeah.
But if we had ignored the 0 here, it would have been an R2, right?
Yes.
And the span would have been R2, right?
Yes.
So since we are in a bigger space, it is some subspace. It is a plane in R3. But if we were in R2, it would have been the entire R2 itself. So it depends on where we are, which space we are in. And based on that, if you have one vector, it is going to always generate a line, whatever be the space, right?
Yes.
If you have two vectors which are not linearly dependent, it is always going to generate a plane, irrespective of which space you are in, right?
That means x 1, 1, 1. So it will have the it will be always a plane in R3 space.
Span of 1, 1, is it?
Yes, ma'am.
This will be a plane or line?
Plane only, ma'am, because S, Y, Z I would have.
No, this will be a line, right? See, any point, how will linear combinations of this set look like?
Ma'am, alpha times 1 plus beta times 1. Okay.
No, this is one vector. Where will this lie? Where will this span lie?
from the single line.
On XYZ lane, on R3.
In R3, it has three components, so it is going to be in R3. So this is one vector in R3. There is only one element of R3 that we are considering.
Yes, ma'am. This is
Ma'am,
just a
then
line.
span of this 1, 1, 1 will be
Alpha times 1,
just
1,
alpha
1,
times
1.
1,
Yeah. It is going to be the vectors in R3 of this form.
Yes.
XYZ components are all same.
And how it's line, ma'am?
Hence, madam, this is not a spanning set for R3, right?
Yes, this is not a spanning set for R3. Why is this a line? Someone asked, why is this a line? Can someone tell?
Ma'am, it's line passing through this point
Because
at 0,
it is just a vector, ma'am, where the tip of the vector is at the point 1, 1, 1.
It is going to be this vector. The span is going to be just all these, right? That entire line.
Yes, yes.
It is going to be the line x is equal to y is equal to z, right?
Yes,
Yes,
yes.
ma'am.
Yes, sir.
Yes.
Fine. So is it clear? Any other questions on spanning
Madam,
sets?
and 1, 0, 0 is not a spanning set for R3, right?
Yes. How many directions do you need to get R3?
3 direction.
Three directions.
So it cannot span, no? You have only one direction here. So anyway, it cannot span R3, right?
Yeah, it is spanning only x-axis.
Yeah.
It is spanning set for x-axis.
Not
Yes, if you... if you take... No, she's asking about this, I guess. 1, 0, 0, right? Or 1, 1, 1.
1, 0, 0.
1, 0, 0 spans the x-axis of R3.
It is spanning set for x-axis, we can see.
Yeah, x-axis in R3, the x-axis of R3. That is why it has three components, 1, 0, 0.
Okay.
If I look at the x-axis in R4, it's going to have 4 components, right?
Yes.
Yeah, that's
And then 4 direction.
For R4, to find a spanning set for R4, you need 4 directions.
But ma'am,
And madam,
if two vectors have different direction, then what can you say about the spanning set?
It's going to be a plane, right?
Plane.
Yes. Suppose you take two vector and but then both have some different direction. So will it be a spanning set in R3 or not?
It won't be a spanning set
No,
for R3, right? Because to generate R3, you need to get space, no? Plane is not enough, right?
3 direct. We need 3 directions.
You need 3, one more you need, right? To get to R3. If you have 2 vectors, you're going to generate a plane. So you can only walk on that plane. How will you reach a point which is outside that plane? For that, you need one more information. One more vector, one more direction.
So madam, we can set at the span of 1, 0, 0, 0, 1, 0. It is a spanning set for a R2.
No. See, it has 3 components.
No, R3.
So you cannot even tell that it is a spanning set for R2 because we are in R3 already. It has 3 components. No, we are already in R3.
Okay. Okay, madam. Okay. Good.
It generates the XY plane in R3. That's all.
Okay.
You cannot say R2. It is the XY plane that is in R3.
And if madam one more component like 0, 0, 1 added in a span set, then it become a spanning set for R3.
Right.
Okay.
Span of 1, 0, 0, 0, 1, 0, 0,
0,
0, 1. What will this give me?
Then it is a spanning set for R3.
R3.
Yeah. The span of this is R3 because any x comma y comma z can be written as x times 1, 0, 0 plus y times 0, 1, 0 plus z times 0, 0, 1. So any point in R3 can be written as a linear combination of these three vectors. So span of this set is R3. So this will be a spanning set. Yes.
Okay, madam. Got it.
What can you say about two vectors in R2, which have both? Both have different direction. Then will that be a spanning set of R2?
Yes.
Yes.
Because two vectors with different directions is going to generate a plane, right?
Okay, but ma'am, if you take 1, 1, and then -1, -1, which have different direction.
No, they don't have. So, by direction means you're not going out of the line, right? They both lie on the same line. Direction in the sense, not the arrow that it points.
Okay, that's what I was trying.
Something like this.
Yes, ma'am. Then, yeah, I got it.
Okay.
Ma'am,
what happened?
Can we say that single element of the R2 vector will be a spanning set for R3?
How? How can it span R3 if you have only one vector? What is the span of this vector?
Like if we expand by any scale, by scaling some scalar.
Whatever scaling you do, you're going to lie in the direction of that vector only, no? It's going to lie on this line only, no? It's not going to go outside this line, right? Whatever spanning you do.
Okay, so that will the vector will lie on the same line, not on the plane.
Yeah.
And ma'am, what about R1? A single point on R1?
You tell me, what is span of, say, 1?
1, it will be 1 minute.
It's R1.
Dot. It's a dot, madam, I think.
What dot?
Yes.
It's R1.
Where is 1? Is it an R or R2 or R3 or R4? Where is it?
R1.
Only a line. Only one. R.
It's an R, right? It's a real number.
Yes.
Can I generate every other number on the real line using this one?
Yes, ma'am.
Yes,
ma'am. How will I get this 3 by 4?
By multiplying it by 3.
Multiplying it by 3 by 4.
How will I get pi?
It's a number line.
Multiply by 5.
Multiplication.
How am I allowed to multiply by pi? How can I do that?
Pi into 1.
Ma'am,
11.22.
Yes.
Am I allowed to do this?
Yes, ma'am.
Yes.
It's a rational. Pi is a rational.
So what? It is a real number. That's all, right? I can do any alpha times 1 where alpha is a real number, right?
Yes, ma'am.
Yes.
Okay. Now what is span of 2?
The same number line.
Same
number line.
How will I get pi from 2?
By multiplying.
Pi by 2.
Pi by 2.
Pi by 2 into 2 is going to give me pi. That's all. So I can generate the entire real line just by using this number, this singleton set.
Yes,
ma'am, that vector you said now that if it is having a different direction, it will be belonging to the R2 space, like like 1 1 and let us say 2 3, which is let us say
1 1 and
2 and -2 and +3, -2 plus 3.
Okay.
So this is not a scalar multiple of, it's like the first vector is not is not a scalar multiple of the other. So here because it contains two components, x and y value, so it is in R2 space, but it is not a spanning set, right?
Why? What is span of these two vectors?
Ma'am, span will be like a continuation of that 1 1 vector in the scene, and the 2 3 -2.
No. You're telling
it will
this
be the scalar multiple of.
It's R2 plane.
Yeah. So, ma'am, then one.
It will not be these two lines, no? See, you're not adding the vectors. If you do this line and this line, you're just doing scalar multiple of this vector and scalar multiple of this vector. But you're allowed to do addition also, no?
Yes, ma'am.
Okay.
So when you add, you will get something here. and then you can add again, like that you will get all the vectors, right?
Okay. Then ma'am, spanning of the 1, 1 and -2, 3, how do I answer? It will be there in R2 space, I understood, but how do I get the spanning of 1, 1 and -2, 3 together?
So you understand span of this is a subset of R2, right?
Yes, ma'am.
You want to know how it is equal to R2, right?
Yes, like if I want to calculate span of 1, 1 and -2, 3, what should I get like in that?
Yeah. So you agree it is a subset of R2.
Yes.
If I show R2 is a subset of span of 1, 1, -2, 3, then it means that the span is equal to R2. Agree?
Yes.
Yeah. So how does an element in R2 look like?
XY.
X and Y.
XY.
If I show that this element belongs to this, then I'm done, right?
Yes.
So how does an element in span of this looks like?
Equals to alpha.
XY plane.
Alpha times 1,
Alpha times 1, 1 plus beta times -2, 3, where alpha and beta can be anything, right?
Yes.
Yes, ma'am.
Can I write x, y as a linear combination of these two vectors? Can I write it as alpha times 1, 1, beta times -2, 3?
Yes.
Yes or no?
Yes, ma'am.
Yes, ma'am.
You will solve this system, right? Alpha minus 2 beta is equal to x. Alpha plus 3 beta is equal to y. Whatever alpha and beta you get, you put that here. That's all, right?
Yes.
So you have written every element in R2 as a linear combination of these two elements.
Okay.
Which means that you have written it. That means it belongs to this set.
It belongs to the spanning of that original vector.
Yeah. So this is proved, which means this is proved.
Madam, means every time we
Madam, what
have to do this to show that it is spanning set.
Can you please repeat that?
Every time we have to do this means calculation to show that spanning set or not.
Yeah.
Okay.
Madam, what if one more vector given in above spanning set like 1, 1, -2, 3 and 2, 2, then it will be a spanning set?
Okay,
Yes,
now
madam.
we have 3 vectors. Is this going to generate space?
No.
It cannot generate space because these are all vectors in a plane, right?
Okay, madam.
So now the question is, what is span of this, right?
Right.
So I know span of this is a subset of R2. Agree?
Agree, madam.
So now let's check the other way around. Can I write any vector in R2 as a linear combination of these vectors?
Yes, madam.
How?
Plus
0
into
0
For x and y.
I already know that I can write it as a linear combination of these two vectors, right?
Yes.
Yes, madam.
So whatever third vector I have, I'll put 0 coefficient. That's all, right?
Yes, ma'am.
Okay.
So
you are
a
also
super-
allowed to put any other value.
yeah, you can put. But then since you already know these two coefficients, put 0 for the third, right?
Okay, madam. Okay, got it.
But ma'am, if you put any non-zero coefficient, then also it will be a spanning set of that R2.
Yeah.
Okay.
Superset of a spanning set is a spanning set. Agree?
Yes, ma'am.
Does everyone agree to this? Superset.
Yes, madam. Now, agree.
You already have a set that generates. You add more vectors, it doesn't matter, no? They are all unnecessary, that's all.
Madam,
Ma'am, it becomes unnecessary because it is in R2 space, right? Because of that only it becomes
Even
unnecessary.
in R3, if you have a spanning set for R3 or by R3, take one line in R3. Can you give me, say this line passes through 1, 1, 1. Can you give me a spanning set for this space? That is the space x is equal to y is equal to z. Can you give me
Ma'am,
a spanning set?
Ma'am, it will be always a line like expansion, like
This
spanning.
is a line. Okay,
Yeah.
fine. This is a line. Can you give me a spanning set? Can you give me a set that spans this line?
Ma'am, like 2,
No.
2, 2,
No.
2,
No.
2, 2.
Right. So you span of 2, 2, 2 gives me this vector space. Agreed?
Yes.
Now, what is span of 2, 2, 2, 3, 3, 3?
Same line.
Same.
Same.
Same space, right? It's the same vector space, same line, right?
Yes.
Yes, ma'am.
This itself is a spanning set. You add more, it is going to give only a spanning set for this. But if you add a vector which is not in this set, like for example, what is span of 2, 2, 2, 1, 0, 0? What is this going to give me?
XY plane in R3.
R3.
Not XY plane, some plane.
Entire R3. Yeah, some plane in R3.
It will be a plane passing through the origin in R3, right?
Okay. Yes, sir. Yes.
Yes, ma'am.
So superset of a spanning set is a spanning set means that doesn't mean just like that. Okay, like this is a superset of this spanning set, right?
Madam, I'm not getting that passing through origin.
Which one?
You said no that we will get XY in R3, plane in R3, which is passing through origin.
Do you agree that span of a set is a vector space?
Span of set means
Span of any set. I had written earlier, no? Span of any set is a subspace. Here, this one. You agree this?
S is a subset of vector space. Okay.
S is any subset. Span of S is always going to be a subspace.
Okay.
Why? Because if you have one vector, the span is going to give you a line passing through the origin. Now tell me, why does it pass through the origin?
Because 0 is always. 0 is always.
In the span.
You can multiply by 0.
You can put all coefficients as 0, no? So 0 is always going to belong to the span, right?
Yes.
Yes, ma'am.
Means, madam, every time 0 will be in the span.
Yeah, 0 can always be written as 0 times v1 plus 0 times v2 plus how many ever vectors you have, 0 times vn, right? Is this a linear combination?
Yes.
Yes, ma'am.
So will this be in span of v1, v2, vn?
Yes, ma'am.
Yes.
Yes, ma'am.
So the spanning subspace, whatever you get, will pass through the origin, right? Means 0 will lie in that, right?
Okay.
Yes, madam.
Okay.
Whatever it is, a line or a plane or whatever we get, will pass through the origin.
Okay.
That is
So,
why
ma'am,
I said
superset of any non-spanning set, I mean, it is not necessary that it is a spanning set. We need to check.
superset of any non-spanning set may or may not be spanning. Agreed.
Okay. But superset of any spanning set is also going to be always going to be a spanning set.
Yeah. So let's take our vector space to be R2. What is span of 1, 0?
X line.
X-axis.
X-axis.
So is this a spanning set for R2?
No, ma'am.
No. What is span of 1, 0, 0, 1?
R2.
R2.
Is this a spanning set for R2?
Yes.
Yes, ma'am.
Yes.
So this is a superset of this set, right? This is not spanning,
Yes,
but
ma'am.
this is spanning. What is span of 1, 0, 0, 1, 1, 1?
Same.
Is also
Same as our.
R2.
Same.
So this is a spanning set, right?
Yes, ma'am.
Once you have reached a spanning set, all supersets will be spanning sets, because this itself was enough, no? We are just adding more information, right?
Yes, ma'am.
But ma'am, the first one, the 1 0, that is not spanning, right? So if that becomes a superset of the second one, which is 1 0 and 0 1, so we cannot say that is also a spanning set, right?
The first one is a subset, no?
First one 1 0 is a
subset of 1 0 0 1.
Yes. Okay. So here that is not the superset, right? So here 1 0 0 1 is a superset for 1 0 0 1 and 1 1, right?
So if this is a spanning set, everything after this will be spanning. Means the bigger sets will be spanning. We cannot tell anything about the smaller sets.
Ma'am, span of 2, 2, 2 is not a spanning set, right? In R3.
Span of?
Yeah, example you are given 2, 2, 2. Is not a spanning set in R3, right?
No. To span R3, you need one more, right?
Yeah.
One more vector. So this is not a spanning set for R3.
Will you always need one more vector?
Yeah, you need 3 directions, no, to reach any point in R3. If you have only 2 directions, you will be on some plane, right?
So can you please explain it geometrically?
Ma'am, like in the first vector also it contains x, y, and z, right? And so on that basis we cannot say it is on R3 because it contains x, y, z, and second also we have x-axis and y0 and z0. So on this basis we cannot say it is spanning in R3.
No, to span something in R3, see, if you want to span R3, do you all agree that span of 2, 2, 2 is a line?
Yes, ma'am.
Yes, ma'am.
What is span of 2, 2, 2, 1, 0, 0?
Ma'am, it is
it's R3. It's R3, ma'am.
No. When
Plane
you have
vector.
only 2 vectors, you can at most reach a plane, no? You cannot go beyond that.
Plane in R3.
Is R3 a plane?
No. R3 is a space. So we need,
so if you have just reached a plane, you want more information to get into space, right?
Ma'am, but it is considering the.
But madam, 2, 2, 2 means we are already in the space, right?
You are in space, but what are you generating? You are in space, I agree. But what are you generating with 2, 2, 2? With just one information, you can generate, you have only one direction, right? Which is pointing towards 2, 2, 2. If you walk on this, where can you go along this direction? You can go beyond this, you can come back, and then you can go in this direction. Can you go out of this?
No.
No. Once you have this 1, 0, 0, that is some other direction. Now where and all can you walk? You can walk along this line, you can walk along this line, and because you know these 2 directions, you can add these 2 directions and walk in between and all that. But still you will be in plane only, right?
Yes.
Okay.
Yes.
You cannot go outside this plane. You can move only in these points. To go outside, you need one more direction.
So adding 0, 0, 1 will lead you to cover up all the space in R3.
Yeah, if you add 0, 0, 1 or even 0, 1, 0, anything is fine. Any one direction. If you do this,
Ma'am, is it mean if we span Rn, so we need n direction?
Yes.
We always need n set, n number of vectors.
Yes.
But ma'am, can you represent it mathematically? Like you took x, y, z in R3, then
you take any x, y, z. If you are able to express it as alpha times 2, 2, 2, plus beta times 1 comma 0 comma 0 plus gamma times 0 comma 0 comma 1, then it means that this is a spanning set. Agree?
Madam, can you please
Yes,
solve
ma'am. Yes.
to beta 1, 0,
Yeah. So this is 2 alpha comma 2 alpha comma 2 alpha plus beta comma 0 comma 0 plus 0 comma 0 comma gamma. This is 2 alpha plus beta comma 2 alpha comma 2 alpha plus gamma, right? So 2 alpha plus beta is x, 2 alpha is y, 2 alpha plus gamma is z. From here we get alpha, y by 2. So when I put that here, beta is x minus y. When I put
Y.
that here, gamma is z minus y. So I can write any x comma y comma z as y by 2 times 2 comma 2 comma 2 plus x minus y times 1 comma 0 comma 0 plus z minus 1 times 0 comma 0 comma 1. Agreed?
Yes,
Yes,
ma'am.
madam.
So when I simplify this, I will get x comma y comma z.
But you can also get it from two vectors, na?
No, how will you get x comma y comma z from two vectors?
Madam, can you please solve up to beta 1, 0,
Beta, okay. I'll do with two vectors and show. We'll stop, means we will get stuck somewhere.
Okay.
So say
It belongs to R, Reena.
Say I have only these two vectors. Now I want to express x
yes.
comma y comma z as alpha times 2 comma 2 comma 2 plus beta times 1 comma 0 comma 0. If I can find alpha and beta, then I am done. Then this will be a spanning set. Right?
Yes.
So this is what? 2 alpha comma 2 alpha comma 2 alpha plus beta comma 0 comma 0. So this is 2 alpha plus beta comma 2 alpha comma 2 alpha, right?
Yes.
2 alpha plus beta is x, 2 alpha is y, 2 alpha is z. Alpha is y by 2 or z by 2? We don't know, right?
Yes, yes, ma'am. Yes, ma'am.
Yeah.
But then we know y and z is equal.
So it will generate a plane where y and z will be equal.
Okay.
Yes,
Won't
ma'am.
give
Not
R3.
for.
Okay,
Yes,
okay.
yes. Got it, ma'am.
So if you have 0 comma 1, it will be in the span. But 0 comma 2 comma 3 will not be in the span because y and z are not equal, right?
Yes, ma'am.
Because if it has to be in this,
Yes, ma'am.
then y and z should be equal.
Ma'am, the
Yes.
third vector which you took, let us say 2, 2, 2, 1, 0, 0, and 0, 0, 1. So it has to be, needless to say, it has to be 0, 0, 1 always, or we can say it can be 0, 1, 0, 1 also.
It can be any vector which is not a linear combination of these two vectors. That's all. Because if it is a linear combination, it's not going to help me, right?
Yeah, yes, because that will be the same vector. That is the expanding of the same vector. But it can not necessarily it has to be 0, 0, 1. It could be anything like 1. It can be 1, 1, 1 also, right?
No, 1, 1, 1 is not going to help me because 1,
It will
1.
be because that will be multiplication of 2, 2, 2. So it can be 1 to 3.
0, 1, 0 is fine.
1 to 3 also can happen. 1, 2, 3.
1, 2, 3 is also fine.
Okay. Thank you.
Any vector which is not a linear combination of these two vectors should work.
Can we say that any three linearly independent vectors will always be spanning set for R3?
Exactly. That's what a basis is.
Okay.
We'll get to that. Is spanning set clear?
Yes, ma'am.
Yeah. So basically,
madam.
spanning set is going to generate the space. You want a set of vectors to generate. You don't want to know whether they repeat, they don't repeat or anything. You just want a set to generate the entire space. In linearly independent, what it means is that linearly independent means what? You don't have any unnecessary information, right? Linearly dependent means you can write one of the vectors in terms of the other vectors. So you can remove that vector, right? It's unnecessary information for us, right?
Yes.
So if you have a linearly independent set, you don't have any unnecessary information. If it is a spanning set, you are trying to generate the space with that set. So what is a basis? It is nothing but a linearly independent set, which is also a spanning set. That is, you don't want any unnecessary information, but you want the required amount of information to generate the space. Is it clear?
Madam,
Yes.
no, I'm not getting
And we can
What is it? You are not getting what?
unnecessary information.
Oh, see, means I'm just using some common man terms, okay? So if I have 1, 1, 1, 0 and 2, 1, can I write 2, 1 as a linear combination of these two vectors, these two?
Yes.
How can I write it?
1, 1 plus 1, 0.
Oh, yeah, straightforward. Okay. So even without this information, I can span R2, right?
Yes, ma'am.
Yes.
Because span of this set itself
Is R2.
means this element belongs to span of this set. So why do I need this information unnecessarily, right?
Yes, ma'am.
It has unnecessary information, so it is a dependent set.
So, ma'am, now what is basis in this?
So you remove the unnecessary information.
Maximum linearly independent.
And these two vectors will become basis.
Yeah. Does this span R2?
Yes, ma'am.
Is there any unnecessary information?
No, ma'am.
So this is a basis.
Okay.
It is a minimal spanning set. What is a minimal spanning set? First of all, what is a spanning set?
Which is in R2 or R3?
Spanning set means span of this set should be R3. If we are looking for a spanning set for R3, span of that set should be R3, right?
Yes, ma'am.
Minimal spanning set means that should be the smallest spanning set. You remove one element from that set, it should no longer be a spanning set. So you're telling that 1, 1, 1, 0, 2, 1. What is the span of this set?
1, 1. R2, sorry. Span of this set is R2.
Now say I remove this vector.
Yes.
What is span of 1, 1, 2, 1?
It will remain R2.
So is this a minimal spanning set? First of all, is this a spanning set?
Yes, ma'am.
Because it spans R2, right?
Yeah.
Is this a spanning set?
Yes, ma'am.
Why?
And because it is, it belongs to R2.
It spans R2.
It spans, yeah, it spans R2.
Is this a minimal spanning set?
Yes.
No, that
Without
is
1, 0 it is, and with 1, 0 it is not.
It is not minimal because even if I remove one element from that set, still I have a subset which is spanning, right?
Yes, ma'am.
But is this minimal spanning set?
Yes,
Yes.
ma'am.
yes.
If I remove one of the elements from this set, will it remain a spanning set for R2?
No.
No, ma'am.
No, man.
This is span of this is not R2. Span of 2, 1 is also not R2.
Yes, ma'am.
So if I remove one of the elements, it is no longer a spanning set. So this is a minimal spanning set. Is that clear?
Yes.
Ma'am, one small confusion here. Ma'am, like 2, 1, x and y value I do have. So it is in R2, but it is not a spanning of R2 because I cannot generate all the elements which exist in
Of
R2.
R2.
Okay. So because of that reason, we are saying it is not a spanning in R2. But,
Yeah.
The moment when we
Can you generate 1, 0 using 2, 1?
no 0, I cannot generate.
Yes.
No, you cannot, no?
I cannot. 0 I cannot generate.
Using
1 I
this,
can
whatever you generate, the first coordinate will be 2 times the second coordinate. That's all. Here, the first coordinate is not 2 times the second coordinate. So I cannot generate this element, right?
Yes, yes. So because of this reason only, I am saying it is not spanning.
Not spanning R2. Yeah.
And
Span
ma'am,
means
like
it should generate the entire space, but it is not, right?
ma'am, like if in question it given let us say 5 or 6 vectors, so each one vector I need to check if I after deleting that particular vector if it is spanning or not.
Yeah.
Then only I will come to know that
It is a minimal spanning set. Yes.
So can we say,
I have a
Madam,
doubt
K,
in this.
Yes, sir. Please go ahead.
for Rn place space, the cardinality of the spanning set is always n.
Cardinality of spanning set can be greater than or equal to n, right? You can add more unnecessary information, no, to keep it a spanning set.
Sorry, it's not spanning set, but base.
Basis. Yeah, basis will be exactly n. Because you want n directions to get Rn, and you don't want any unnecessary information, which means n is needed.
Ma'am, the minimal spanning set will be the basis, right?
Minimal spanning set will be a basis. Perfect. Yes.
Okay.
Yeah. Someone had a doubt, right? Someone was asking something and I interrupted.
Yes, ma'am. But in the activity 4.1 question number 8, the first option says that if a subset S of R2 contains only 2 elements, then S is a basis of R2.
You tell me if that is true or not.
And because the basis is a minimal spanning set, no, ma'am, then how can it not be a basis?
What is span of 1, 1 and 2, 2?
It should be linearly independent.
This is not R2, right?
Yes.
It has 2 elements. Can it be a basis for R2? It is not spanning R2, no?
No, ma'am.
Yeah. So is what minimal spanning set clear? Is there anything on the chat?
Ma'am, for that previous question, can we say 2 independent vectors means we can say it's R2, no, ma'am? Spanning set, 2 independent.
Yeah. If it is a spanning set and if it is linearly independent, it is a basis, right? And for R2, we need only 2 elements. Why we need only 2 elements?
Because we only
can a set containing more than 2 elements be linearly independent in R2?
No, ma'am.
No, madam. No.
That's why a basis cannot have 3 elements for R2. A basis of R2 cannot have 3 elements.
Then a basis of R3 can have 2 elements?
You tell me. Can I generate R3 with 2 elements?
Yes.
How? We couldn't know.
We couldn't?
We did know something.
It won't be a spanning set, but it might be a linearly independent, but it will never be a spanning set.
See, I couldn't generate R3, no, with these 2 elements.
But there's a question in 9 also that 2 element of a vector's space is a spanning set of V.
What is that?
Is a span.
Depends on that, no.
X equal Y minus Z. 4.1 question number 9. Option 3rd.
This is a different subspace. No, this is not R3. This is a subspace of R3.
Okay. Then if it is R3, then it must have 3 elements.
Yeah.
Okay.
So what was I telling? Yeah. What is minimal spanning set clear?
Yes.
What is a maximal linearly independent set?
It's same as base.
No. What does
if
it
we
mean?
add any more elements, then it will be linearly dependent.
Yeah, it will lose its independence if we add more elements. That is a maximal linearly independent set.
Madam, when we were talking earlier, when we were talking about dependent and independent, then we were equating it with 0. But now we are not doing that, right?
No, now only we are talking about independence, dependence. No, we were talking about spanning set all this while.
No, means in week 3, independent and dependent. We were taking linear combinations and equating with it 0.
Yeah, that is how you check independence and dependence.
But now we are not doing that, right?
No, now I am telling geometrically, so we are not doing that. If we write down mathematically, we will do that only. We'll equate that to 0, linear combination to 0 and all that.
Okay.
I was just telling direction, this and that, no. So it just went off with words. If you write down how they'll be independent or dependent, if you check, you have to go by the definition. You'll put it equal to 0 and then you have to find out the coefficients, all that only.
Okay.
So do you agree that a minimal spanning set has to be a basis?
Yes, madam, perfectly.
And a maximal linearly independent set has to be a basis?
Yes, ma'am.
So a linearly independent set means what? You don't have any unnecessary information. That is the maximal linearly independent set. If you add one more information, it becomes unnecessary, which means that the set that you have has the required amount of information and it doesn't have any unnecessary information. So it is a basis.
Ma'am, then maximum linearly independent, that is equal to minimal spanning set, and that is also equal to basis.
Right.
Okay.
A basis is both maximal linearly independent as well as minimal spanning. If you have a set, if you can prove that it is maximal linearly independent, that's all. It is a basis. You needn't show that it is a spanning set. If you have a set and if you can show it is a minimal spanning set, then that is a basis. You needn't show it is linearly independent. Fine?
Yes, ma'am.
Which of the following sets are maximal linearly independent sets in R2? Is the first one maximal linearly independent?
No, ma'am.
No,
ma'am.
No.
Why not?
Because it
Because
has
it is
equal
not only in X.
Spanning.
Span in only
Okay.
X direction.
But if I can add one more vector and still the set can be linearly independent, right?
Yes, ma'am.
That is why it is not maximal linearly independent. Maximal linearly independent means I add one more vector, the set becomes dependent. Then, but I can still add a vector and make the set remain independent. So it is not maximal linearly independent. What about option 2?
No, ma'am. It is linearly
It is
dependent.
dependent.
It is not even linearly independent. Then only talk about maximal. First of all, a maximal linearly independent set has to be linearly independent. That itself is not satisfied in option 2. What about option 3?
Yes, it is, madam.
Once you add one more vector, it is going to be dependent. So option 3 is maximal linearly independent. What about option 4?
It is also dependent.
The set itself is dependent. What about option 4?
It is maximal linearly independent.
Yeah.
Correct.
Correct. What about minimal spanning sets of R3? Is one a spanning set for R3?
No, madam.
Not even a spanning set.
No.
Forget being minimal. Option 2?
Yes, madam, it is.
Yes.
Why?
Because it satisfies that it is a in R3.
Why is it a spanning set, first of all?
Spanning set is R3 here.
Because it is span to R3.
How can you prove that it spans R3?
because
X,
we
Y,
can't.
Z can be expressed in.
You write
Because
any
it is
XYZ
independent.
as alpha times 100 plus beta times 110 plus gamma times 111, and then you can find out what is alpha, beta, gamma. You can directly find gamma. Gamma is Z, right?
Yes.
Yes.
Alpha plus beta plus gamma is X. Beta plus gamma is Y. Gamma is Z. So from here we have beta is Y minus Z. So alpha is X minus Y
minus Z.
minus Z or plus Z?
Plus Z.
No, plus Z.
Minus Z. So beta will be here. Oh, I think it will be X minus Y, right? There is a Z here that will get cancelled. Yeah. So
And we can
option
also
2.
observe it by just looking that no two of them are scalar multiplication of other.
Right.
Yes.
What about option 3?
Yes, right.
Yes.
Okay.
Correct.
Option 4.
No, ma'am. And third one is the scalar multiplication.
Oh, you can add the first two vectors and get the third.
Get the third one.
Okay. What about option 5?
No, ma'am.
It is also dependent.
When you talk about spanning sets, you shouldn't tell dependent, independent. You should tell that if I remove one of these vectors, it will still be a spanning set. That is why it is not minimal spanning. Yeah, but minimal spanning, maximal linearly independent, all that is same. But the question asks just for minimal spanning set. So in that sense, we can answer. Fine. Okay. So a basis is a linearly independent set that also spans the vector space. A set which is both linearly independent and spanning is a vector space, is a basis. And a basis is equivalent to a maximal linearly independent set and a minimal spanning set. Okay, now tell me, how will I find a minimal spanning set if I have a spanning set? I have a spanning set, say V1, V2, Vn. This is a spanning set. How will I find a minimal spanning set?
But ma'am, by removing one of the set from that and check whether they are giving the spanning sets still after removing that particular.
Yeah. So if this is a minimal spanning set, the problem ends there. Suppose it is not minimal spanning set, it means that one of the vectors is a linear combination of another vector, right? There is some unnecessary information in this set, right?
Yes, ma'am.
So you will remove that. Say Vn is the unnecessary one. You will remove that. Will this still be a spanning set?
Yes, ma'am.
Yes.
Yeah, because I just removed unnecessary information, no? I didn't remove any necessary information. So it will still be a spanning set. Now you check whether this is minimal spanning. That is, if you remove any information, will it lose its spanning property? You check. If not, then you go ahead and remove. There is some more unnecessary information. You remove that step by step till you reach a minimal spanning set. Yes.
Ma'am, any order we need to follow? Like
no, you just see if you have say 2, 0, 0, 1, 0, 0, 3, 1, 1, 0, 0, 1. Is this a spanning set for R3?
Yes, madam.
Yes, ma'am.
Yeah. Is this a minimal spanning set?
No, ma'am.
No.
Can you quickly identify one vector which is unnecessary?
2, 0, 0 or 1, 0, 0.
Yes, madam.
Yeah, just remove that. There is no particular order. It can be anywhere. Just quickly identify and then get rid of it.
Okay.
Yeah. And can you tell me if there is only one single basis for a vector space or there are more?
Only single, madam.
Only single.
Really? Only one base?
Ma'am, there can be infinitely
many bases.
Yes, ma'am.
Is this a basis for R2?
Yes,
No,
ma'am.
Yes.
Yes.
Why not?
Yes, ma'am.
Yes, it is.
Yes, ma'am.
Is this a basis?
2002 is also.
Yes, ma'am.
Is this
Yes,
a
yes,
basis?
madam.
Yes.
Yes, yes,
Yes,
madam.
ma'am.
Yes, ma'am.
Why complicate so much?
Infine.
2002, is this a basis?
Yes, ma'am.
Yes.
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 3003?
Yes, ma'am.
Yes.
Yes, ma'am.
Infinitely many.
So infinitely many bases is possible. Did you notice that all the bases will have exactly the same number of elements?
Yes, ma'am.
Yes, ma'am.
That is called the dimension of the vector space.
Ma'am?
The number of elements in any basis for the vector space is called the dimension. Whatever be the vectors, I need two directions to span R2, right?
Yes, ma'am.
Ma'am, how do we find a set of the cardinality of base of a matrix set?
I'll tell you all that. So we'll go step by step. Okay, we'll get there. Then what else did I want to tell?
Ma'am, this basis one which you told now, like we can have multiple bases, but when it is different element for a particular set, if I do have been given a particular set of set question, okay, so find the how many bases can be possible. So in that particular given vectors, I do have only one basis or maximum linearly independent or minimal spanning space set, right? I cannot have multiple bases for that particular vectors.
No, I have R2 here. I have given you multiple bases, right?
Achha, if you are asking R2, then I do have multiple. But if I have given a question, let us say aapne like 1 0 0 1 and let us say 2 3, I do have. So in that case,
From there, yeah. From there, if you want to build a basis, it will be
only
means
one,
if you're
right?
given,
Only one.
yeah.
Yes.
So given a set,
That's
if
what
it
I
is
was saying.
linearly independent, you can add vectors and make it a basis, right?
Yes.
To make it generating spanning set.
Yes, yes.
If
So
you are
in
given a
that
spanning set, you can remove vectors and make it linearly independent, right?
independent and also the minimal spanning set or
Will
also
be
the
basis.
basis. So it will be
Yeah.
only one, but not no multiple things.
If you want to retain those vectors, then only one. Yeah. Okay. So how will we find the basis for subsets of Rn? That's one thing. So see, what is it? What does basis do? How many elements are there in a vector space?
Infinite.
Infinite.
Because if V belongs to a vector space, alpha V belongs to vector space. Alpha is any real number. So there are infinitely many elements. What is a basis doing actually? Did we look at any basis with infinitely many elements till now? No, we are all looking at finite dimensional vector spaces. Finite dimensional means basis is having finite number of elements. So you are picking some elements. Say this is R4. You are picking 4 elements that forms a basis, right?
Yes, yes, ma'am.
What does this basis tell you about the vector space?
Like within that confined space, the minimum number of elements required.
Can you tell what this element is just by knowing these 4 elements of the basis?
Yeah, line.
Can you?
Like the vector space.
No, not line.
To
Okay,
which
let's
vector
come to
space it
R2.
belongs?
Let's come to R2. How many elements do you need in R2 to for a
Two
basis?
elements. Two elements.
Okay, say suppose these are the 2 elements that form a basis. Can you tell about this element with these 2 basis vectors?
It will be linear combination of.
So any element in R2 is going to be a linear combination of those 2 vectors, right?
If it has more than 2 elements.
No.
To more than 2
Any
vectors, sorry.
element
More
in
than
R2.
2 vectors. For example, if I do have 2 vectors, 2 elements, constituting one vector. But if I do have another vector, but that should be a linear combination of the existing two vectors.
Right? No. But if I have a set 1, 0 and 0, 1, is this set enough to understand R2 completely?
Yes, ma'am, because X and Y I do have.
Yes, ma'am.
I can put any X, Y as X times 1, 0 plus Y times 0, 1,
Yes.
right? So if I know these two vectors, I know the entire R2,
Yes,
right?
ma'am.
So from infinitely many vectors, we have come down to just two vectors, which is going to give information about all the other vectors, right?
Yes.
So that is what is nice about a basis.
Okay.
Even though there are infinitely many elements, you pick a few elements which represents the entire set. It's like picking up a class leader, no? If you want to communicate something to the class, you just tell it to the leader and the representative or someone, and that person spreads the information. So that person is enough to give us all information about the class.
Okay.
So you just pick some vectors which is going to give you information about the entire vector space.
How
Yes,
the basis can be
Ma'am, ma'am, like yeah, how does these two vectors is giving entire R2 space? Because R2 space I can have, let us say 2, 3 and 4, 5 also I can have.
Yeah,
no?
but even
So
if
that
I
is
have
also
2, 3, I can write it as 2 times 1, 0 plus 3 times 0, 1, right? So using these two vectors, I can get this vector.
And
Okay.
if x, 0 is another vector space, is another subspace, and y, 0 is another, is 0, y is another subspace, then will their union be a subspace?
You tell me, will it be a subspace?
It should be, ma'am.
Why should it be? X-axis, y-axis. Why should their union be a subspace? If you add two elements in this, if you add two elements from the x-axis and y-axis, will it remain either on the x-axis or y-axis?
No, but they are a subspace of R2.
So what? If I add 1, 0 and 0, 1, they are both in this set, right? 1, 0 belongs to this union, right?
Yes.
0, 1 belongs to this union, right?
Right.
If it is a subspace, their sum should also belong to this union, right?
Right.
But their sum is 1, 1. 1, 1 neither lies on the x-axis nor on the y-axis.
Okay. But the intersection 0, 0 will lie.
Yeah. So the union
will be a subspace.
May or may not be subspaces, but intersection will always be a subspace.
Okay.
Fine. Yeah, someone else was asking it out, right?
Yeah. See, we saw that spanning set is infinitely many. Right? Minimal spanning set may be infinitely many, but how the basis may be only finite?
No, bases. There are infinitely many bases, but the number of elements in each basis is only finite.
Okay.
Dimension is same.
Yeah. The cardinality of each basis is same. There are infinitely many bases, but the cardinality of all those will be the same. And that is called the dimension of the vector space. Is it clear?
Okay. Then can now you tell me about how do we calculate a basis for a matrix system?
We will first do Rn, then we will go to n cross n. Is that okay? Once we do Rn, you will have an idea of what has to be done, then matrices will be fine.
Okay, but today's time is over now. Like it's 2014.
I can continue. I don't have a problem. You have any other session? Any other courses session?
No, ma'am. No, ma'am.
Then we can continue.
Okay.
And tomorrow also I will
actually,
only continue. Like tomorrow 8 o'clock we have a session, right? I'll continue from
Yes.
whatever we left here.
Okay. No
Yeah.
issue.
Ma'am, we have a statistics 2 session now, so can we leave?
Yeah, please.
Yeah. So
Anyway, we are recording this session and we'll change the YouTube link on the calendar and put this recording on the calendar, in the sense on YouTube.
okay. So what else will you be discussing today?
We can stop here if it's okay with everyone. No, I was just thinking of doing some examples for bases, how to find bases.
Okay, ma'am. Anyway, I'll check the link.
Record.
Yeah.
Yeah,
Okay.
watch it on YouTube. Yeah.
Okay. Thank you, ma'am.
So yeah, we have a vector space. V is a vector space which is defined as this. Where does this vector space lie? R2, R3, R. Where is it?
R3.
Yeah, we have X,
R3.
Y, Z, 3 components. So this is a subset of R3. Now what is this? Can you tell me what this is? Is this a plane, a line, or R3 itself?
It's a line,
R3
ma'am.
itself.
Can it be R3 itself?
It's a plane.
Actually, no line.
These are 2 lines, ma'am.
This is one line, this is one more line. Okay. And then what will happen to the intersection? Okay, let's look at it. Okay. So if you get span, if you find a basis for this and if it has only one element, it is a line. If we find a basis that has 2 elements, it is a plane, right? And if the basis contains 3 elements, it is R3 itself. Agree?
Yes, ma'am.
Yes, ma'am.
Yeah. Okay. So how will we find the basis? Our strategy is very simple. Start with a spanning set. Means somehow find a spanning set and then convert it into a linearly independent set. Fine. Then we would have reached a basis, right? Or convert it into a
Yes,
minimal
madam.
spanning set. As simple as that. Minimal spanning. That is, you make sure that it is linearly independent. That's all. Now, this is the set. Set of all x, y, z such that 2x plus 3y is equal to 0 and y plus 5z is equal to 0. So what can we tell about x, y and z from this? What can you tell about x from this?
X is minus 3y by 2.
Minus 3y2
Minus 3y by 2.
y.
We'll put everything in terms of y. So what can you tell about z here?
Minus
Minus
y
y
by
by
Minus 1 by 5.
Right. So can I write this set as set of all minus 3 by 2y, y, minus y by 5?
Yes.
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 Y
ma'am.
can be anything, right? There is no restriction on y.
Right.
So can I write this as set of all y times minus 3 by 2, 1, minus 1 by 5, where y can be anything?
Yes.
Yes, ma'am.
Yes.
Okay.
What is this set?
This set is a minimum spanning.
No, what is this set? Can you write it as span of something?
Yes, ma'am.
Yes.
Span of what?
Span of
Span
V
of 3 minus 3 by 2.
by
1.
2.
Agree?
By 5.
Yes.
Yes, ma'am.
Because span of this set is alpha times this vector, right?
Yes.
And that alpha is y here, right?
Yes.
Now I have found a spanning set for the vector space, right?
Yes.
If this is the minimal spanning set, then this will be a basis. Agree?
Yes.
Ma'am.
Is this minimal spanning?
Yes.
Yes, ma'am.
Why?
No, ma'am.
Why not?
Because We can add another element.
No, minimal means you have to remove, not add.
Yes.
If we remove, then it is not.
If you remove, how many elements does this set have?
Only one
element.
If you remove that element, what will you have?
Empty set.
0.
Will that empty set generate this space?
No, ma'am.
No.
So is this a minimal spanning set?
Yes.
Yes. So is it a basis?
Yes.
Yes.
So what is the dimension of that vector space?
1.
So what is it? Line or plane?
Line.
Line.
Yeah. One dimensional means it has to be a line, right?
Yes.
So the one who said it is not minimal spanning, is it clear?
Yes, ma'am, because we have defined something here.
Minimal spanning, to check whether it is minimal spanning or not, you shouldn't add, you should remove.
Yes, ma'am, and it is the situation because we have two different conditions on the set.
Okay. So,
like x 2x plus 3y equals z. 2x plus y equals 3.
Okay.
2x plus 3y equals 0 and y plus 5z equals 0. These are the two conditions. That's why we got one element in the minimal spanning set.
Okay, fine.
Am I right?
Agreed. But you tell me this, 2x plus 3y is equal to 0 and 4x plus 6y is equal to 0. Even now I have two conditions. Will this give me a line?
This will give a single line, man. This will give a single line.
Means you will have only this, right? Because the second condition is nothing but 2 times the first condition, right?
Right, ma'am.
Yeah. So you have to make sure whether there is any redundancy, whether there is any unnecessary equations, and then only you have to find the spanning set. Okay. So why have I included this? I wanted to include something else. Okay, let's do it here. Now suppose the vector space is set of all x comma y comma z such that x plus y is equal to 0, or let's put x plus y plus z is equal to 0. Where is this subset of R, R2, R3, R4? What is it a subset of?
R3.
Why?
Because it has 3 coordinates.
It has 3 components and hence it is a subset of R3. So let's find a basis for this. So we want to, our strategy is find a spanning set and then make it into a minimal spanning set. So what is this? Again, same thing we will do. X plus y plus z is equal to 0. Now can I express x in terms of y and z? Can I express all the 3 coordinates in terms of one of the variables? Like how we did in the previous case?
No, ma'am.
No, ma'am.
Minimum 2.
No, ma'am.
We need 2, right?
Yes, ma'am.
So shall we put z is equal to x minus y? Minus x minus
minus x minus y.
Yeah.
So we can express z as minus x minus y. So it becomes x comma y comma minus x minus y. Where x and y can be anything, right?
Yes,
yes, ma'am.
Yeah. So from this, how do we get a spanning set? Can I write this vector as x times 1 comma 0 comma minus 1 plus y times 0 comma 1 comma minus 1?
Yes, ma'am.
Yes,
I'm just taking x out, and wherever x is there, I'm putting 1. Wherever x is not there, I'm putting 0. Similarly, I'm just taking y out because x and y are independent, right? You are allowed to choose x and y as and when, as you wish, right?
Yes, madam.
Can I write this as span of some set?
Yes, ma'am.
What is that set?
1 comma 0 comma minus 1 and 0 comma
0,
1 comma minus
1 comma minus 1.
Why is it so?
Because
x and y we have the scalars.
So this is nothing but a linear combination of these two vectors, right?
Yes, ma'am.
Yes, ma'am.
Now now we have found a spanning set. Is this minimal spanning?
Yes, ma'am.
Why?
Because if we remove one of the element of the set, we cannot get the
Spanning set.
spanning set.
So if we remove one of the elements, say I take this, what do I get? What is the span of this?
X,
No.
comma 0, comma 1.
Minus
X, comma
XZ
0,
plane in
comma
R.
minus x. No, not the XZ plane. This is a line, right? Oh, no. This won't be a line. Oh, no, yeah. This will be a line, right? This will be a line.
Yes, ma'am.
And this is the subspace. Z is equal to minus x.
Minus of x.
Y is equal to 0, right?
Yes, ma'am.
Yes.
Is
Yeah,
this
madam.
same as the set that we got? Means we started with?
No, ma'am.
No.
Why the y is equal to 0 is not compulsory in the set that we started with, right? Y can be anything, right?
Yes, ma'am. Y can be anything.
Yeah. So this is not that set that we started with. So this is not a spanning set. So this has to be minimal spanning. Agree?
Yes, madam. I agree.
So is that a basis?
Yes, ma'am.
That's
Yes,
just
ma'am.
one basis. If instead of putting z is equal to minus x minus y, if I had put x is equal to minus z minus y, I would have got another basis, right?
Yes,
ma'am.
And if I had put y is equal to minus x minus z, I would have got another basis. So depending on what variable you're choosing to keep as dependent, you will get a different basis. But can you see that all basis elements will satisfy the condition x plus y plus z is equal to 0?
Yes, madam.
Yes, ma'am.
Naturally, right? Because the basis elements should belong to the vector space, right?
Mm-hmm.
Ma'am, can I ask a
What is the
Can I ask a doubt in activity 4.2?
Sure. What is the dimension of this vector space?
2.
2.
So what is this vector space?
Plane.
Line, plane,
Plane.
space.
Plane.
Yeah.
Plane.
Right. So what was the doubt in activity?
Question
Which
number
one?
7, ma'am.
Okay.
4.2, ma'am, not 4.1.
Oh. 4.2, question number 7. Huh.
So, ma'am, how
So you're really interested in matrices, right?
Yes, ma'am. How are you calculating the basis here?
Okay, which of the following sets forms a basis? Let me do one more Rn and then get to matrices, okay?
Okay, ma'am.
Yeah, I'll tell you, means there is a connection, that's why.
Okay.
Okay, so how are we finding dimension of a vector space? By finding out a basis,
Yes, ma'am.
right?
Cardinality of a basis.
Yeah, we find a basis, start with a spanning set, convert it into a minimal spanning set, and then find a basis, and then find the number of elements in the basis to get the dimension. So can you find a basis for this vector space? What is this vector space? First of all, identify what the vector space is. Where does this vector space lie?
R4.
R4.
Yeah. So there is one condition, x minus y plus z minus w is equal to 0. So how many variables can I keep as dependent and how many can I keep as independent?
3.
3 is what? Dependent or independent?
Independent.
Independent.
So I can write this as, say, x is equal to y minus z plus w. So this I can write as set of all y minus z plus w, comma y, comma z, comma w, where there is no restriction on y, z and w. So what will be a basis? Or what will be a spanning set?
Y minus Z plus W.
No, what did we do? We picked out the variables, right? Whatever the independent variables were, we picked them out. So you'll put y times what vector?
0, minus 0.
No, y. There is a y here, there is a y here.
Yes, 1, 1, 0, 0.
And z times?
Minus 1, 0, 1, 0.
Plus w times?
1, 0, 0, 1.
Yeah. And y and z and w can be anything. So we have got a spanning set. Is that minimal spanning?
Yes, ma'am.
You can either check whether it is minimal spanning or not, or you can check that it is linearly independent. In either case, it will form a basis and the dimension will be 3. Can you see that the dimension 3 is nothing but the number of independent variables?
Yes, ma'am.
Yes, ma'am.
Yeah. So can you do similarly for this?
Yes, ma'am.
There are 2 conditions. Okay, so you do this. We'll do the matrix example. We will do the AQ problem today, and then we will discuss more matrix examples tomorrow. Is that okay?
Okay, ma'am.
And then we have to cover rank also, I guess. Something, yeah, rank.
Rank and dimension. Rank dimension for Gaussian elimination. Using Gaussian elimination.
Yeah. Okay, so we'll do this example. Which of the following sets forms the basis of the vector space 2 cross 2 lower triangular real matrices? Okay, fine. Now what is the vector space?
2 cross 2.
2 cross 2 matrices of the form A, B,
0.
Lower triangular means upper part will be 0. A, 0, B, C. A, B, C can be anything, right?
Yes, ma'am.
Yes,
this is the set.
Yes, madam.
If you know A, do you know the entire matrix?
No, ma'am.
No, ma'am.
No, madam.
If you know A and B, do you know the entire matrix?
No, ma'am.
If you know A, B, C, do you know the entire matrix?
Yes.
Yes, madam.
So how much information is needed?
3 elements.
3.
So the dimension will be 3.
Okay.
So how will we check that? Yeah, this is how you look at it and find out. But how will you formally check that? You will try to find a basis and find out the number of elements for the basis, right?
Right. And if it was said that the matrix is a diagonal matrix, then the dimension would be 2?
Yeah.
Okay, all right, ma'am.
So you find a spanning set. Can you find a spanning set for this set of matrices? Like how we did here.
Okay.
Matrix A 0 0 0.
A times
1 0 0
plus V into
V
0 0 1 0.
0 1 0. C into
Plus C into 0 0 0
0 0 0 1.
Yeah. A, B, C can be anything, right?
Yes, madam.
Yes, ma'am.
So this is nothing but span of 1 0 0
1 0 0
0 0
0 0 1 0
0 0
0 0 0 1.
right? So
Yes,
are
madam.
all these lower triangular matrices?
Yes, ma'am.
Yes, madam.
Yeah. You should make sure that all the entries of the basis are elements of the vector space.
So, ma'am, if we find the basis of a scalar, then the dimension will be 1.
Yeah. Now, how will you check that this is minimal spanning or linearly independent? Let's check whether this is linearly independent or not.
Determinates. Row echelon. Reduce row echelon form.
No, but how?
No,
These are all
private
matrices.
elements.
Ma'am, we can form the system of linear equation by taking any coefficient with alpha times 1 0 0 0 plus beta.
Right. You shouldn't find determinant of these matrices. That is not what we saw earlier, right? If you had 3 vectors in R3, 4 vectors in R4, then you form a matrix. But this is not, this is a vector, this is another vector, this is another vector, right?
Yes,
You shouldn't find the determinant of these matrices. You should go by the definition. Alpha times the first vector plus beta times the second vector plus gamma times the third vector is equal to the zero vector. What is the zero vector of this vector space?
0, 0, 0,
0,
0.
0, 0, 0, 0.
The zero matrix. Now, if you can show that alpha, beta, and gamma should definitely be 0, then it is a linear.
Can it is
Linearly independent.
It is, right?
Yes,
Because
madam.
alpha is appearing only here, beta is appearing only here, gamma is appearing only here.
Yes.
So this is a basis. So it is 3-dimensional.
Okay, madam.
Thank you, ma'am.
So shall we stop here? We will do more examples tomorrow and then we will continue with rank.
Yes.
Yes.
Madam,
Yeah.
madam, just a last doubt. Whatever you taught to us, everything is I will got it. But what is the application of all this thing in data science, madam?
You will study actually. You will see these applications. Once you go to MLF, Machine Learning Foundations, you will actually be continuing with mathematics basically. And then from there you will see applications. Means linear algebra forms the basis the foundation for data science is linear algebra and statistics. Whatever you study in Math 1, Math 2, Stat 1, Stat 2, that forms the basis for entire data science. So you will be minimizing
madam.
some function and all that. You will, as you go forward, you will see applications.
Okay.
Yeah.
Okay.
Okay, so maybe I will. Can we quickly solve this problem also, because this is the only one that's left unsolved?
Okay, ma'am.
Okay, ma'am.
Let's solve.
So what is this set? It is the set of all x, y, z, w such that
X plus y minus z minus w
Equals
is equal to 0.
x
X, y,
minus
z.
y minus z plus w is equal to 0.
W 0.
Yeah. Then what do we do to this system?
Defined by a variable. Defining a variable.
Find the spanning set.
Yeah, find the spanning set. How will we do that? We have a system of two equations.
We
Ma'am,
will
can
define
we add
variable
these
for one variable.
When you add them, what will you get?
2x
In a 3.
to 0.
2x plus x minus z equals 0.
Yes, yes.
You will get this. But is this the vector space or do you have some other condition? Are you telling it stops here or is there something else that we have to write?
X equals z.
Okay, let's put x is equal to z. But does it stop there?
No, ma'am, in the original equation, we can substitute this x equal to z. Then
you shouldn't stop here because see, you're just getting x is equal to z. So you're telling that 1, 2, 1, 4 belongs to this vector space from this step, right?
Yes, ma'am.
But does this element actually belong to the vector space? X plus y should be equal to z plus w. Is that satisfied?
No, ma'am.
No, ma'am.
So there is something wrong. We are missing out on some equation. So that is because you just added them, but instead you should substitute this and see what else are you getting. So when you substitute, you're getting y is equal to
Madam.
w also, right?
Yes.
Madam, please, could you please repeat again? I can't get it.
So you added these two equations and wrote down this condition, right?
Yes, madam.
But you just added these two. You have not made use of both these equations, right? You're not using all the information that is available from both the equations. You just added them and then got some information out of it, right?
Yes, madam.
So if I stop here, suppose I add these two equations and tell this is the vector space. 1, 2, 1, 4 belongs to this vector space according to this condition, right? Because x is equal to z. Agree?
Yes, madam.
But does
Yes,
this
madam.
belong to the vector space actually? If it belongs to the
Oh,
vector
okay. No,
no,
madam.
right? X plus y should be equal to
No.
z plus w. That is not satisfied, right?
Yes, madam. Ah, yes. Agree.
So you're missing out on something.
So,
What is it that you missed out on?
we,
You add the two
we should add y equal
Ah.
to w. Y equal to
So
w.
you originally have the two conditions. But is the second condition needed? Means, is it necessary to put both the conditions?
Yes, ma'am.
It is actually not necessary because you have added these two. Means that you can remove one of the equations, right? When you're solving a system of linear equations, x plus y is equal to 1, x minus y is equal to, or
yes,
2x minus y is equal, or 2x plus y is equal to 2. When you do this, what do you do? Okay, let's say 3y is equal to 2.
If we find one solution, we put in only one equation and find the another variable value.
When you multiply the first equation with 2, that's what you will do, right? To subtract and all that.
Yes.
So once you do this, you're ignoring this equation, right?
Yes, madam.
And then you're dealing with these two equations. You subtract these two, you will put y is equal to 0.
0.
Right?
X
So
is equal.
once you use these two, you've got some information, you go back and put. So like that, here when we add those two equations, we have got one information.
So shall we subtract two equations, then we got
You
the
can
Z
remove one of the
equal.
equations. It is not necessary to keep both the equations. You add them, you get one information. And then you keep one of the other two equations. You needn't keep both. If you keep both also, it's okay. It's redundant. See, can you see that if you consider these three equations, you can get this equation from the other two equations?
Yes.
That's what we did, right? We added those two and got this equation.
Okay.
Okay, fine. Let's
Okay.
keep all the equations. Let's keep all of them. You will see what happens. So what do we get from here? We get x is equal to z, right?
Yes, ma'am.
If we madam keep all three equations, then we get not get a minimal spanning set, I think.
Right. Yeah. Now x is equal to z. Can you put x is equal to z in the other two conditions?
Yes.
Yes,
Yeah,
ma'am.
because the
That-
line below both the conditions are satisfied. And.
That
So
will
what will
give
you get from the first equation?
y equal w.
From the second equation?
Same thing.
Again y equal to w.
Yeah. So now you see it is unnecessary to keep both.
Yes.
Yeah. So you will get y is equal to w.
So we will just move forward with x equals z and y equal w.
Yeah. X comma y comma x comma y.
Right.
X and y can be anything. R. So what is a spanning set?
X into 1, 0, 1, 0 plus y 0, 1, 0,
1.
Yeah. X and y can be anything.
Right.
So this is nothing but span of those two vectors.
1,
0,
0,
1, 0.
1,
0,
0, 1.
Will this be a basis?
Yes, ma'am.
Yes, ma'am.
Yes,
You can
yes.
check for linear independence or minimal spanning. And you can actually check that these two vectors satisfy those conditions. 1,
Yes,
0,
madam.
1, 0 and 0,
0,
1.
0, 1, 0, 1.
0.
X plus y is z plus w for both. And x plus w is y plus z. X plus w is y plus z. X plus w is y plus z. So this is a two-dimensional subspace. This forms a basis. Is this clear?
Yes, ma'am.
Yes, ma'am.
Yes, madam.
Okay.
No, I did not.
Huh? It is not clear, is it?
Yeah, like how to
What
solve,
part is not clear?
like x equals to z and y equals to w. How?
That is clear, is it?
No, I did not understand here.
Okay. So you have two equations, two conditions given
Yes.
here, right? So that becomes these two equations.
Yes.
So I somehow want to bring all these variables, means I want to see how many variables I can get rid of,
Yes.
right? Can I get rid of W from here?
Yes.
I can write it as W is equal to X plus Y minus Z,
Yes.
right? So can I put that W in the second equation?
Yes.
I'll get X minus Y minus Z plus X plus Y minus Z is equal to 0,
Yes.
right? So what do I get? Y gets cancelled. 2X minus 2Z is equal to 0,
Yes.
right? So what do I get from there? X is equal to Z, this one,
Yes.
right?
Yes.
Now, I'll go back and substitute, right? X is equal to Z
Okay.
in this equation. I want to get rid of as
Yes.
many variables as
Yes.
possible. Huh. So when I put X is equal to Z, I get Y is equal to W.
Okay, now I get it.
Yeah. Can I reduce it any further?
No.
No. That's all. So we'll do more examples tomorrow to find bases and all that, and we'll go ahead with rank.
Thank you so much, madam, for this.
Thank you.
Thank you so
ma'am.
much, ma'am.
No, thank you.
Good night.
Good night.
Good night, madam.